It's your friendly math tutor, Miss C here, and today we are talking about absolute value. So here are the basics. So absolute value of a number is that number's distance from zero. So when you take the absolute value of a number, you always get out a positive value, and that is because distance is only measured positively. So there's not some other magic that happens that, it's the absolute value, so it's always positive. It's because we're looking at distance. So let's go ahead and practice finding a few distances from zero, aka taking the absolute value of zero. So the absolute value of 5 is asking how far is 5 from zero, and that is 5 units. The absolute value of -10 is saying how far is -10 from zero? It's 10 units. The absolute value of zero, how far is zero from zero? It's 0 units. The absolute value of -3 says that we are 3 units from zero, and the absolute value of 552 tells us that we're exactly 552 units from zero. Now that we have down what absolute value is, distance from zero, let's look at the absolute value as a function. So this is the parent function of absolute value. Y equals the absolute value of x. As a reminder, a function passes the vertical line test. That means that for every x value, there is a single y value. Now let's look at what's always true for absolute value functions. Absolute value functions always have a vertex. They always have an axis of symmetry. That means that this graph is completely symmetrical, and they always have a y-intercept. If you've studied quadratic functions in the past, you're going to notice that these are all very similar. The graphs look different, but the behavior is similar. This is the table of values centered around the vertex of the absolute value function. The vertex is 0, 0, and you're going to notice the symmetry of the y values as you move out from 0. This is expected, right? Because the absolute value measures distance, and -1 and 1 are exactly the same distance from 0, so you would get the same y value. -2 and +2 are exactly the same distance from 0, so the same y value, and so on. Moving on to the graph of the absolute value parent function, we have the graph of y equals the absolute value of x. We've already looked at these values. Here is what the graph looks like. A lot of people describe the absolute value graph as looking like a big V. So we see that our graph is centered at 0, 0. So that would be our vertex. We see it on the table right here, and it's the yellow point on our graph. And then out of that vertex, we have what appear to be two lines going in two different directions to create a V. So that's the graph of the absolute value. You can see there's a line of symmetry as well. That's this dashed blue line that if we were to fold the graph on that line, it would fold on top of itself. So that means that the values are completely symmetrical about the line of symmetry. And we might be asked what the vertex and the axis or the line of symmetry are. So our vertex on this graph is our lowest point. It's 0, 0. We would call this point the minimum value of our graph. If the graph is reflected, it becomes the maximum point on the graph, the tallest, biggest point. And our axis of symmetry, the equation is x equals, so all vertical lines have the equation x equals, and it's the x coordinate, that's this one, of our vertex. So these three things, the vertex being at 0, 0, the vertex being a minimum, and the axis of symmetry being equal to 0, are always true for the parent function. Now, let's look at some transformed values or some transformed graphs, because that's going to help us better understand the absolute value function. So in this graph, we have y equals the absolute value of x plus 3. If you look at the table, you're going to notice every y value has 3 added to it. That makes me think that my y value is moving up or is getting bigger by 3, hence moving our graph up. So the big idea here is whenever you have a number added outside, that's the key, the absolute value bars, if that number is positive, it shifts the graph up that number. If the number is negative, it shifts the graph down that number. So in this case, this is what our graph looks like. You can still see there is a vertex, and everything is centered around the line of symmetry. The only thing that's changed is our graph has been shifted up 3 units. And that's not just the vertex has been shifted up 3 units, every single point has been shifted up 3 units. That places our new vertex at 0, 3. That's this yellow point, still a minimum. And our axis of symmetry has not changed. It's still x equals 0. All right, our next transformed graph, y equals the absolute value of x minus 2. So you're going to notice that everything is within the absolute value bars, and that is a key. When it's inside the bars, our graph is shifted left or it's shifted right. And the way that we tell whether it's shifted left or right is we look at what the x value needs to take on to make what's inside the parentheses equal to 0. In this case, to make what's inside of the absolute value bars, not the parentheses, equal to 0, x has to be 2. So this shifts my graph to the right 2 units. Okay, so let's have a look at that. So there's my graph. Every point has been shifted to the right 2 units. So if you look at the y value, normally that was at 1, it's been shifted to the right 2. So you could think of this as every value on our parent function being adjusted by 2. So what is our new vertex? That has changed. So we are now at 2, 0, because we've been shifted right 2 units, still a minimum. Our x-axis of symmetry has changed to x equals, our x value here is 2, so x equals 2. All right, let's look at the next transformed function. All right, so we have y equals 2 times the absolute value of x. And what we can tell by looking at this equation is that this 2 is being multiplied outside of the absolute value bars. And what I can think about mathematically is the y value is going to get 2 times bigger than the parent function because it's being multiplied by 2. That means that each side of my graph is going to be 2 times steeper. So here's the big idea. Any number multiplied outside of the absolute value bars, and outside is the key word here, vertically stretches or shrinks the graph. So think of this as a vertical stretch because the y values are growing faster. That means that the V is getting narrower. It's getting closer to the y-axis. So let's take a look at this, the table of values. You can see we're still centered at 0, 0 here, but the values, this used to be a 1, it's now a 2. This used to be a 2, it's now a 4. This used to be a 3, and now it's a 6. So it's growing. Every y value is 2 times bigger than they previously were. So just for reference, if I were to sketch on the parent function, let's see if I can do it as well on this side. This is what the parent function looks like. You're going to notice that 2 times bigger. If I come over here, this is 2 times bigger. So you're going to notice it's considerably steeper. And the bigger this number gets here, so like if it were 10, it would be even steeper. It'd be 10 times as steep. Okay, so what this does not change is it doesn't change the vertex, which still is 0, 0, and it's still a minimum. Nor does it change the axis of symmetry, which remains x equals 0. It simply changes the steepness of the graph. If this is a number greater than 1, it's a vertical stretch because it's stretching faster, the y values are getting bigger. And if it's a number between 0 and 1, so essentially a fraction, it's going to widen and it's going to get farther from the y-axis. All right, we also have one other type of transformation that we see often, and that happens when we have a negative outside, I don't know why my pen's not working, in front of the absolute value bar. So this is negative times the absolute value of x. What you're going to notice on the table is it turns every single y value negative. So this is called a reflection, and it's reflected about the y-axis. So the key here is it has to be outside of the absolute value bars for it to be a reflection. If it's inside, since our graph is symmetrical, you don't really notice the change. But if it's outside, it turns our graph upside down. So our vertex still is 0, 0. But this time, instead of it being a minimum, it's a maximum. So it's going to be the highest point on our graph. And our axis of symmetry still is x equals 0. Once again, the only difference is every x value is now negative. All right, now that we have the fundamentals of how absolute value graphs are transformed, let's practice solving a few equations. Okay, let's get solving. So a couple of things to notice here is we have the absolute value of x plus 2 equals 4. This graph has been transformed. We are looking at this part right here that tells us what our function looks like. It's been shifted up 2. And what we're really looking at when we solve this graph is we're looking at where this graph intersects with the line y equals 4. So that's what this equation means. So we're going to see that we have 2 intersection points. I just circled those. So let's go ahead and solve for this, and I'll show you how you find both answers. All right, so our first step is we're always trying to get our variable by itself, but this time we're trying to get the variable within the absolute value bars by itself so we can de-absolute value it or get rid of the bars. So I'm going to start by subtracting 2 from both sides. When I do that, I get the absolute value of x equals positive 2. This is how I get rid of the absolute value bars. I have to set up 2 equations. One that says x is equal to positive 2, and one that says x is equal to negative 2. That is how we basically get rid of the absolute value bars as we set up 2 equations. What's nice about this is it just gave us our 2 answers. So if we look at the graph, we can see that we have, this is x equals negative 2 right here, and this one is x equals positive 2. So what this answer means is everywhere we see negative 2 and positive 2 for x, we have a y value of 4. All right, so the way we drop the absolute value bars one more time is we set up 2 equations, one where whatever is left on the left side of the equation is equal to the positive of what's on the right side, and one where whatever is left on the left side is equal to the negative, right? Because we end up with a negative and a positive. Okay, this one's a little bit different, and this will show you why drop where and when dropping the absolute value bars matters. So in this case, we have the absolute value of x minus 3 equals 1. So as a transformation, we're looking at this part here. So just let's make sure we remember what happens to our graph. Our graph shifted right 3 units. And what this is actually asking us is where does that blue part of our equation, that's the graph of our absolute value function, intersect with the line y equals 1. So once again, we have 2 solutions. That's almost always the case unless you're finding a solution that's the vertex or you're asked to find something that doesn't exist on the graph. Okay, so this one's a little bit different than the last equation because everything is trapped within those absolute value bars. So the first thing we have to do is get rid of the absolute value bars. So that means I'm going to write one equation, x minus 3 equals the positive version of what's here. Oops, I went the wrong way. I was trying to change my pen color. And then the absolute, we do the same thing, but instead of it equaling the positive one, we know it also has to equal negative 1. All right, so let's go ahead and solve. I'm going to add 3 to both sides. When I do that, I get x equals 4. So we can see that right here, this is where x equals 4, this point, and that gives us a value of 1. And now let's solve for our other value. We're going to add 3 again. In this case, we get x equals positive 2. That's this value right here, and we can see that this is 2 and this is 4, but they both have a value of 1. So when x equals 2 and when x equals 4, we get y values of 1. All right, our last equation in this set is we have our function half times the absolute value of x equals 3. So our transformation here is that this is a vertical shrink by a factor of half. That means our graph is 2 times wider, right, every value has essentially been shrunk by half, because that's what our scale factor is, or our factor is. So that means this graph is growing much more slowly, which means it's much more wide. So we are looking at where this graph intersects. I forgot to change that. With y equals 3, you can see that that's y equals 3 is right there. So we have two intersection points, unsurprisingly, once again. So let's go ahead and solve this. So our first step is to get the absolute value bars by itself. And in this case, you can divide by half, or you can multiply by the reciprocal of half. That's always my favorite way to do this, but either way works. So I'm multiplying by 2 on both sides. When I do that, this makes a 1 here, so I'm left with the absolute value of x here. 3 times 2 is 6. You'll get the exact same thing if you divide by half. Now I'm going to get rid of my absolute value by setting one of the equations equal to positive 6 and setting the other equation equal to negative 6. And once again, because there's nothing inside the absolute value bars, I'm finished. I have a solution at positive 6. Let me grab my highlighter. And that solution is right here. My other solution is at negative 6, and that solution is right here. So you can see both of these values, x values, have a y value of 3. Make sure to subscribe for more math videos. Till next time, remember, you've got this.